Okay, so this is the last piece on pointers for a while. And just to recap, where have we been? So we talked about pointers to built-in types, things like pointers to integers and so on. Then we saw that array names in certain instances, in certain contexts, behave like pointers. We saw pointers to one-dimensional arrays, two-dimensional arrays, names as pointers. We saw function pointers and their use. And now we're going to look at dynamic memory and the relationship of pointers to dynamic memory. And this is actually very, very useful. So let's take a look at the following example. Normally, if I want to declare an array, let's say of size 3, so I would do something like this. I would say, look, I have an integer array. Say the name of the array is A, and it's of size 3. Now, what you have to realize is this declaration is in the program at the time that the program, of course, is going to be compiled, right? You write this in your source code, and then the compiler knows, and it knows certain things. It knows that, first of all, I have something called A, and because of the brackets, it knows that A is an array, and it also knows the size of the array. It's going to be of 3, and it's going to be of 3 ints, right? We could use the right-left rule to determine that. So everything is known about the array at compile time. So the compiler can then optimize. It knows exactly how much space to allocate and so on at a given time. But look at this example over here. Let's say I declare an array of size n. And depending on how the program runs and the interaction of the program with the user of the program, we ask the user of the program, as the program is running, give me an n. How much you need an array? How big is the array going to be? Now notice it's not known. What's known at compile time is that this is going to be an array, right? Because it says it has the brackets over here. But how big the array is going to be is not known at compile time. C++ does not allow this. Okay, that's not legal. It'd be nice if it did, but it doesn't. Now, why not? Well, the thing to realize that C++ is a descendant of C. It has to be compatible with C, and C didn't allow it. So why did C not allow it? Because one of the important design decisions in C was it had to be super fast. It had to run very, very quickly. And one of the corollaries of that was that you want to depend on runtime allocation of space, and anything that depends on runtime, you want to minimize that. So if you need an array, decide beforehand how big it is, and I'll make sure that you get it, says C++, says C and C++. But something like this dynamic memory allocation, dynamic meaning at runtime, that's characterized by this kind of thing, C didn't allow and C++ does not allow. But you still want to do this. And it's going to be very useful in many applications to be able to dynamically allocate memory and make the thing that you allocate actually behave like an array. So we're going to now distinguish between two kinds of memory. One is called automatic memory. Automatic memory is the kind of variables, kind of memory utilization that you all know and love and have been using up till now. And dynamic memory, and this is the new thing we're going to look at. So automatic memory is the kind of memory you get when you have to make all the declarations about the sizes and the types at the time you write the program, and the compiler knows it when it compiles. So when you say that I have an integer I, it's going to allocate the memory for you, and it's gonna do it automatically. It's called an automatic variable because you're not explicitly requesting I. You're just telling the compiler that this object that I'm going to be using later on in my program is an integer variable. So it knows the size, say 4 bytes, 8 bytes, depending on the system you're running on, and it knows what kind of things it can do with it, right? It takes an integer, so I can add, subtract, multiply, divide, and so on. It knows all these things, and it's known at compile time. And again, the important thing is that it's automatically allocated for you, right? When it enters the scope or where it's defined, it automatically gives it to you. So what does that mean? What does scope mean? Scope means where the variable is known. So for example, I would do something like this. I'd enter some kind of scope. I open it with a curly brace and I close it with a curly brace. So if I say I have an integer I, where is that integer I known? What's the scope of it? What's its lifetime? Its lifetime is within the scope before I came in here, right? Up here, even though the compiler saw it, right, because it compiled it, it doesn't have any meaning. I can't use I outside this scope. So it comes into existence over here, and as soon as the flow of control hits the closing brace, then there is no more I. So if I were to try to do C out I let's say over here, that would be perfectly okay. But if I tried at the end of this, right after I exit the scope, to say C out I, the compiler would say, I have no idea what you're talking about. This variable is unknown. Okay, so that's what we mean by automatic variables. These are the ones that automatically get allocated at the time that they're encountered, and their lifetime is within the block, within the scope that they're defined in. Now, what about dynamic memory? What does that mean, and how do you use it? So in order to get a new integer, I would use something like this. Okay, now what in the world does this mean? What's going on over here? So in order to fully understand this, what I'd like you to do is in your class notes, you have some empty space here on page 54. And I'm going to draw a diagram for you. And I want you to, that diagram is going to explain what is happening. This is a very, very important thing to understand how this works. So let's just take a look at this. So what does your program look like? In other words, when you run a program and you put it through the compiler and all the disparate pieces get linked together and it's ready to run, so it's going to sit in the RAM in contiguous space. It's going to look just like this. This is a very important diagram. So imagine this is the space in the RAM that's going to be allocated to your program as the program runs. So what's in here? What kind of things are in here? So first of all, the code is going to be in the place that's out. Notice it's going to be placed. The code will be over here. So by code, we mean all of the functions that your program is going to be utilizing. So for example, of course, your main program, any function that you define. If you pound include IO streams, you say C out I and so on. So all the IO functions, any other libraries, pre-built functions that you bring from someplace else, that's going to be over here. That's all the code is going to be in here. And that's called the code segment. Okay, so there's part of the of this piece over here. Now, just make sure you understand what's going on. This is the operating system. When your program runs, the operating system is going to allocate to your program a fixed size of contiguous. Contiguous means there's no holes in here. Contiguous space for your program to utilize as it's running, and nobody has access to this, just your program. Okay, so it's made up of these pieces, right? One piece is called the code segment. And all the rest, right? All the rest are various, it's called the data segment. That's where all the data is going to reside. And what do we mean by data? So we'll see. There's various kinds of data that your program can manipulate as it runs. Now, in the data segment, there are a number of sections in data segment. So this next one, let's say, and I just want to point out, this is just, of course, a schematic. It's not necessarily going to be in this order. Many ways to describe, but this is just conceptual. This is what happens when your code is running. It has all of these pieces over here. So one part of the data segments where the data is going to be stored is where the constants are going to be kept and where the statics are going to be kept. Let me write a little bit bigger so you can see what's happening. The const and the statics. So that's kept in a separate area in the data segment. What do we mean by a const? So for example, let's say if I say integer I equals 3, so I'm declaring this variable I, and I'm initializing it to 3, right? But later on in my program, I can say I is equal to 5, and the value of I is going to change. So I is a regular variable that's not a static. But if I were to say const int I equals 3, then I'm declaring the variable I to be an integer, but I'm saying that that's a constant value. So that if you were to go later on in the program and try to say I is equal to 5, the compiler would complain. You can't do this, and it won't compile, because you're doing something that's illegal, right? So why do I want consts? Well, many times, let's say, for example, I say something like, I have double, let's say pi is equal to 3.14. So that's the mathematical value of pi, right? If I just use this number in my program, it sort of looks like some magic number. Nobody really knows what that is necessarily. But if I give it a name, pi, then I can say, you know, pi times r, and whoever's reading my program recognizes what this thing is. And it has the advantage that if I declare pi to be const, if I say const double pi, then nobody could change this. So I can't inadvertently change it. So it helps the readability of my program. And then, of course, later on, we'll see there are other reasons that you would want to declare things to be constants. But right now, let this suffice. So if I declare var to be a constant variable, it gets stored in some very special place. What do we mean by static? So static is one of these words in C++ that is really overloaded. It has many uses in many different places. I think some of you might have seen the use of static in the lab, but just very quickly, and we're going to get to this later on. We talk about functions and recursion and so on. If I have some kind of function, let's have some kind of integer function f, you know, some integer I, whatever, and let's say I declare a variable, you know, I say I want to count how many times it's going to be someplace. So I say I have an integer variable called count, and I initialize it to 0, and then I say count plus plus, right? And every time I come to this function f, I'd like to increase the count. And so then I can say, tell me how many times I've been here. So I can say cout count, right? So every time I come in, I would hope that count is going to get incremented. And then I can see I've been here 1 time, 2 times, 3 times, so on. Of course, this is not going to work. Why won't it work? Because, again, it has that notion of scope, right? If this is a function, then all the variables in this function, both the arguments and the local variables, the scope is local to the function, meaning that as soon as I exit the function, they just sort of disappear, right? We'll see how that works, but they're not there anymore. So the next time I come into my function f, I'm going to get a new variable count. It's going to get to 0. It's going to initialize to 0, and then it's going to go count plus plus. Every time I come through, this is going to really print 1 each time. So that's not what I want. So is there any way to get variables that I declare within a scope, within a function, for example, so that when I leave the function, I somehow manage to keep the value of that variable between invocation of the function? And that's where the keyword static comes in. So if I were to say something like, you know, I have an integer variable, and the name of that variable is count, and I want to initialize it to 0, but I say static count. The word static, S-T-A-T-I-C, static count. Let me write it so it's clearer. Static count, and say static int count. Static int count equals 0. So I initialize it, and then I say count plus plus, right? And then I go on with the rest of my function. So by declaring it static, what happens essentially is that the first time, this will happen once and only once. And that's this initialization of count to 0 will happen the first time this function f is called. And count is not going to be kept with all the other automatic variables, right? Remember, this is an automatic variable because it gets automatically created for me and so on. It's going to be kept someplace else. And that's in this area over here where the constant statics are kept. What about the other automatic? Where are they kept? Well, not here. And we'll see that in a moment. So that's the idea of static. Okay. What else happens in here? So then we have something called the runtime stack. That's over here. So I'm going to simply write runtime stack, RTS, runtime stack. Runtime stack. The runtime stack is where the automatic variables are kept. So when we get to functions, we're going to talk about stacks in great detail. But basically what a stack is like, it's sort of imagine it's a way of storing information. It's a data structure where it stores things like you would do, there used to be, imagine stacking dishes, right? So imagine dishes come out of the dishwasher, and the first dish comes out. Here's the first dish. You put it over here, and then the second dish, put over here, and the third dish over here, and the fourth dish. And you're stacking all these dishes on in a stack, right? Stacking one on top of the other, right? And what happens is every time a new one comes in, you put it on the top of the stack, right? This was the first dish came out, and this is the last dish. But when you take the operation of putting things onto a stack like this in computer science is called pushing onto the stack. You're pushing something onto the stack. So I put one dish, and I push the second dish, and I push the third dish. When I take something off the stack, notice, first of all, you don't go in here and just sort of, imagine you have 20 dishes here. You don't grab this dish. That's not what you do. When you want to take something, you always take it off the top of the stack, and that's called popping the stack. So this is a way of storing information such that the last in is the first out, LIFO. Last dish that goes in is the first dish that goes out. And that's what happens over here. In this runtime stack, automatic variables are kept on a stack. And so as you come in, and we'll see details later on, but that's basically the idea over here. So as you come in to some, imagine I have a situation like this. I have some integer, and I say I is equal to 10, and then I say, float f is equal to 3.5, right? And then I open a new scope, and I say integer k is equal to 12, and I say double z is equal to 15.3, and so on. And then I close the stack. So basically, so I have here a scope. What happens is, as the compiler reaches these things, these statements, it sort of allocates space in RAM, something along the following lines. It's first going to give you place for the variable I, and then it's going to give you place for the variable f, and then it's going to give you space for the variable k. It's pushing. This is like a stack, right? A stack of locations for your variables inside the RAM, and then it's going to give you space for k, and then it's going to give you space for z, right? So stacks one on top of the other, and then so it's pushing, right? As it gives you space for the variable, it allocates space by pushing one on top of the other. And what happens once you exit this scope? So it's going to pop this stack, right? It pushed the variable, the locations onto the stack, and then it's going to pop it. So when you come out of here, z is going to go away, and then k is going to go away, and the stack is going to basically look like this, right? So this happens automatically. These are automatic variables. You don't have to ask for space. You just use those declarations, and it's going to allocate. So this is the runtime stack, right? This is where the variables are going to be stored. So what do we have so far? We have the code segment where all the programs are. Then we have in the data segments, we have where the constants are stored, and the runtime stack where the automatic variables are. And then the rest of this place, again, this is a simplification, but the rest of this place is where the dynamic memory is going to be stored, right? So this is the place for the dynamic memory. And usually there's two parts over here. One is where, these conceptually also, it doesn't have to necessarily be physically, but conceptually there's two parts of this memory. One we're going to be calling the heap. That's one, and the other one is going to be called the free store. Now, usually the free store is the place where the C++ dynamic memory is going to be allocated from, and the heap is where the C style memory is going to be allocated. But in C++, you can get both kinds. We'll talk more about this in a little bit. And dynamic memory is going to allow us to, at runtime, allocate some space, and it's going to allow us to solve that problem of getting arrays of variable sizes, right? So that's where we're heading. So let's go back and take a look how that looks. Let's say that I want to get some dynamic memory. I want to get a variable I so I can store something in this variable I. So I would say this. I would say something like this. Now let me explain. This is strange. So let me explain what happens when we do this. What's going on exactly? When I want a normal, we call normal, when I want a automatic variable, the kind that we've been using all the time, say a variable I would say integer I, right? That's the declaration. What happens here in the runtime stack is that, as we saw before, it's a stack, so I will be allocated at runtime, but automatically, some variable I, and if I now say I is equal to 15, so then 15 is going to be put in this place. Remember, all this stuff that you have here, it's all in the RAM. But there's a way of getting a variable, a place to store an integer, not in the automatic way. This is the way we've always been doing it. But we can do the other way to do this is using the dynamic memory. And what I would do there is there's a new keyword called new. And then I would say the keyword, I would say new. New what? I want an integer. So I would say new int. What's going to happen is the memory manager is going to go to the dynamic memory. It's going to go in here and find some place for me that's going to be able to store an int, a place large enough for an int. Now, but what does it return? What does it return? So it's going to return to me, the programmer, it's going to return the address in the RAM, but specifically in the heap, in the free store, where we want to use the word heap, though. It's going to return the address of where it found memory for me. So since it's returning an address, and it's going to be the address of an integer, so I'm going to say, let's say IP, an integer pointer, and what is this integer pointer? It's going to be an int star, right? Let's just call it I to make it parallel the example over here. So this is the second way to do this. And what happens when I do this, I say int star I. So I is going to be an integer variable. I is going to be a pointer variable. And it's going to have the address of where the memory manager found place for me in the RAM. And if I wanted to diagram this, it's going to look like this. In the RAM, I'm going to have a place called I, right? This is going to be I. Originally, this was I, because I can't call both I, right? It's just another example. But this place is not, it's not an integer. There's going to be a pointer to an integer. And what it's going to do is it's going to point to a place in the dynamic memory area where the dynamic memory manager found me place for my integer. And if I want to put a 15 in here, I would have to say in star I, right? Since now I is a pointer, right? I have to dereference the pointer and say star I is equal to 15. So there's two ways to get a place to store an integer. This is the normal way, by saying I is equal to 5. And the other way is to say I is a pointer to an integer, call new, tell it you want a place for an integer, and it'll give you that place, and then dereference I to put the value that you want in there. Now, why in the world would you want to do this? Generally, you would not. You want to do it just for an integer variable. But this turns out in other places, we'll get towards the end of the semester, we'll start, we'll build classes, and we'll see how this is extremely useful. And it's also going to solve the problem that we saw before. But before we go on with this, to see that, let's just take a look at how this thing works in more detail. What kind of language support do you get for it? So as we just saw, to get dynamic memory, I use the keyword new, and then I say new what, and I say I want a new integer, it returns a pointer, and I have to have a place to store the pointer if I want some. So likewise, if I want a new floating point value, so it's the same basic idea. So I say I want a new float. So I say new float. And what it's going to do, it's going to return a pointer to me, to the place in the heap where it found the float, and I got to store it someplace. So let's say FP stands for floating point pointer, FP. So FP is going to get the value of that pointer. But what's the type of FP? It's going to be a float star. Okay, so that's the basic idea. Now, there could be a problem if we do this, and it can be quite severe. So let me explain what that is. So as we saw, this is the memory layout. And if I do this, right, if I say this thing over here, right, if I say I want a new integer and I'm going to store it in IP, in I, so I, where does I live? Let's say you have a 15 in here, so there's a 15 in here. Where does I live? I lives in the runtime stack. And that means it's an automatic variable. And that means when it goes out of scope, it'll disappear. Where is the 15 stored? When I say star I is equal to 15, so the 15 lives in here, not in the runtime stack, but it lives in the heap. So let's take a look at the following scenario. What's going to happen in this case over here? So I open some scope like this, and then I say exactly that. I say star in star IP, I is equal to new int. And so then it gives me this integer over here, right? And then I say in there, in star I want you to put a 15. And so that's going to put a 15 right over there. But then what happens, right? I opened up a scope over here, and then I keep doing whatever I want to do, and then I end the scope over here. So the question is, what lives where? This is a very important question. Where does the variable I, that's the pointer variable, where does the variable I live? Well, the variable I lives on the runtime stack, right over here, right? As we saw, the I lives over here. So what that means is that the lifetime of I is basically just to the end of the scope. So that as soon as we hit the bottom of the scope over here, I disappears. There's no more I. Right? This goes away. This guy here goes away. But what about the location in the heap, which is also part of the RAM? All this stuff over here is part of the RAM. What happens to that? What happens to that location over here? Well, that does not go away. This you explicitly asked for by saying new. Then the memory manager went out and looked for what it is for a place for your integer. And then when you lose I, you lose any connection to this, and you have no way of not only retrieving this, but this is a big, this is sort of sitting there, and it's basically going to be used up, and there's no way that anybody could get it again. That is a problem. Essentially, what happens is that you lost this memory. It's a big, big problem, and that there's a technical name for it, and it's called a memory leak. Right? The memory basically disappeared, and you have no way to get it. So there has to be some way in C++ that when you get some memory from the dynamic memory allocator, from the heap storage, there has to be some way to give it back, and in fact, there is. So let's take a look what that might be. Just before we go on, there's a quick correction. I inadvertently put a 15 in here. Of course, this doesn't belong in here. There is no 15 in here. All right, this is in the heap. The 15 was here, but while we had it, this is going to be I, and I does not have a 15. I, of course, has the address in the RAM where it is. So this is some kind of address. The 15 goes here. All right, I just want to clear that up. I made a mistake, and I noticed that after I finished the recording. Okay. Besides the keyword new that allocates memory for us, there is another keyword called delete, and what that does, it returns the memory to the pool. That's very important, right? So we saw what a memory leak is. It's when you lose a pointer because the pointer lives in the runtime stack and the actual memory lives in the heap. And so by saying delete before you go out of scope, then you won't lose it. So here's an example. So let's say we're in some scope, right? We're in a scope over here, and we say int star I is equal to new int, like we did before, right? And then we do whatever we need to do with it. But before, what we saw that when we go out of scope, we were going to lose the area in the that was allocated by new. But if what we do now is we say delete I, right? You see over here, there's delete. We say delete I before we go out of scope. What that's going to do, well, I is a pointer, so it will pass this pointer to the memory manager, the heap manager, and it'll say, I don't need this anymore. Reincorporate it into your memory pool. So that's an important idea. As we'll see later on, this could cause some problems. So, for example, you want to do this in a function as well, right? So let's say we have a function. This whole thing happens in a function, say. So let's say I have some function, say it returns an integer, some function, whatever it is, and we open up the scope, and we do exactly what we did before, right? We say I have some integer pointer I is equal to new int like before, right? And then we say, we use I, and so on. At the very end, before we return from the function, right, before we return over here, before we go out of scope, we're going to say delete I. So that's no problem, right? We saw this before. Now the scope is part of a function. But let's say, down the line, somebody does some maintenance on this thing, and then they put something else in here, and then they return over here, right? So beforehand, what you would return from down here, you would hit the delete. But if somebody, let's say it's a big function, and they don't realize that they are supposed to delete the memory, or they simply forgot about it, you end up returning from the middle of the function, and even though you allocated space on the heap, it will never get returned, so you're going to get a memory leak as well. So it's problematic, and there are ways to handle it, and we'll see those ways later on in the semester. Okay, so that is if we want to get memory for a single variable, which most of the time is not all that useful. What we saw, the original question was, how do we get memory for an array at runtime? How do we do that? And so the answer is there's another form of new that works with an array, right? And that's the second one over here, right? We didn't get to it yet, but this one right over here. So this one over here, and so we can say I have an integer n, and then right over here I can say cin n, and then you give me a 5, and I say give me a new, not only an integer, give me an integer array, and this will be 5. And what will happen is in the runtime stack there will be a variable a, and that's the pointer variable, and it's going to be pointing into the heap, and in the heap I will have the place for that array. And so this really behaves like an array. As we'll see an example in a little while, I can use the array name because we know that array names are basically pointers to the beginning of the array. Even in this case, I can use the array name as an array. And we'll see that soon. But just like you have the same problem here in terms of memory leaks, right? If this is defined in some kind of block, right? If it's in a block, as soon as we get out of the block, so the variable n, the variable a that you have over here is going to go out of scope. So it's going to lose this pointer. It's not going to point to here anymore. It's going to be inaccessible. And then this big array is going to be leaked. And you can imagine this is just an array of size 5. Imagine it's an array of size 5,000 to 5 million. Okay, so just like there is a delete for a single variable, there's also a delete for an array. And you have to be careful with so you say delete, and I tell C++ that that's an array, and then I say what the pointer is. So in this case, the pointer's name was A, so I say delete A. It's not what you would imagine. You wouldn't say delete A bracket, say delete bracket, because that's sort of the name of the function here. So the bracket means I'm deleting a pointer to an array, and A is that pointer, right? And here is the example that we saw before. We define an integer n, we're reading it in, we get an array of size n, and then I delete it. So here's an example of how we might use this thing, right? So for the case of a single variable, this is the first example. For the case of a single variable, IP is pointing to an integer, and I say, give me an integer, and that's what we saw before. And then I say star IP is 5. When I print out star IP, I'm going to print 5, and that's what we saw. And how about for the array? So this is actually it's the same idea. We come over here and we say I have a, and a is a pointer to an integer. So it looks like this in memory. Here is the runtime stack, right? The runtime stack. And the runtime stack, I have a, and a points to an array in the heap of size 3, right? And now what I do is in this for loop, notice how I can use a. Since a is a pointer to the beginning of an array, I can use a sub I to point to the ith element of the array even though the actual array resides in the heap, right? So this is a strange thing. It's sort of a very schizophrenic object here. It lives in two places. It lives in the runtime stack, and it lives in the heap. Part here, right? Part here. And so the problem is, if this were to go out of scope before you delete this, then we leak, right? So and so I goes from 0 to 2. So what's going to happen is it's going to put 0 times 10, which is 0. 1 times 10, it's going to put a 10. 2 times 10, it's going to put a 20. So it fills it up with 0, 10, and 20. And then we just go through the loop, and we can print it out. So notice we use the array that we got from the heap in exactly the same way that we did when we had a regular array. But notice what we don't have over here is we don't delete, but that's only because you're ending the program right here, so it'll automatically release that memory. But if you were doing this in some other scope, or if you were doing this, right, if you put this thing here in a function, then when you exited the function, instead of this being a main, let's say it's some other function f, and you did not, let's get rid of this guy here, if you did not do a delete a, you have to say delete, bracket a. If you didn't do that, and this is some function, when you came back from the main program, then this thing would have leaked. So that's basically the idea. This is the idea of pointers pointing to dynamic memory, and it's going to be very useful. And in fact, at the very next video, I'm going to give you a program to work on that will show how you actually could use this in a real program. It's going to utilize what we did before, and the only new thing will be the dynamic memory.